Okay, so I welcome you all to the lecture series. So we're going to talk about curvature in this lecture as well as the subsequent lectures. And this is the last section of our course on Riemannian geometry. I would like to begin today by briefly reviewing what we know about Gaussian curvature for surfaces. And the main purpose would be to connect the calculations of Gaussian curvature and various aspects of it to our formalism of connections and associated one forms and two forms. So that is the aim of this lecture, so that moving forward for the subsequent lectures you have some motivation and understanding of what we are going to define and why we are defining it. Okay. All right. So let's begin. So we are going to consider surfaces in R3. These are embedded surfaces. And we of course have a Riemannian metric on the surface, basically because you have a Riemannian metric on R3, which is also the Euclidean metric. I'm going to often make the use of notation that the Riemannian metric is the Euclidean metric. That is because the tangent space of R3 is globally trivial. So any tangent space at any point can be identified by translation to the tangent space at 0, which can be further identified with R3, and that has the Euclidean inner product. So that's what I mean by the Euclidean metric or the Riemannian metric on R3. And sigma being a submanifold, an induced metric is there on sigma. So remember from the theory of surfaces, one of the results that you have seen in a course earlier, and we have also discussed this in our tutorial session, is that a smooth curve lying on the surface is a geodesic if and only if the acceleration is perpendicular to the tangent space. Okay, so this is much more than saying that the acceleration is perpendicular to the velocity. I mean, that's a rather easy fact that you can deduce simply by saying that the velocity of a geodesic has the property that its norm is constant. In other words, the speed of a geodesic is constant. But if you take the norm square of velocity and you take d by dt of that, you simply get gamma dot product with gamma double dot. And that would say that the acceleration is perpendicular to the velocity, but this is saying something more. It's saying that the acceleration is actually in the normal direction to the tangent space. Okay. And now since the tangent space is dimension 2, the perpendicular, the orthogonal complement of the tangent space has dimension 1. So the acceleration necessarily has to be a scalar multiple of a chosen normal vector field. All right. Okay. So if you wanted to see what the formalism of connections, namely when we say connections here, of course we mean the Levi-Civita connection or the Riemannian connection nabla on sigma. So we want to see what this Riemannian connection on nabla on sigma looks like. We have seen that if you have a manifold which has a Riemannian metric, so it has a Levi-Civita connection, and it has a submanifold, then you can take the usual Levi-Civita connection of x with respect to y, and then you have to project this onto the tangential part of the submanifold to get the corresponding Levi-Civita connection of the submanifold with respect to the induced metric. So what do I mean by this? Well, remember that the usual Levi-Civita connection on R3 is nothing but the standard covariant derivative, meaning given vector fields x tilde and y tilde, you consider dy tilde. So y tilde has three components, three functions, one in the d by dx direction, the other one in the d by dy directions, and the third in the d by dz direction. So d of that is going to be a 3 cross 3 matrix because it to differentiate each one of these functions with respect to x, y, and z. So this matrix acts on the vector field x tilde, which again has three components. What you'll get is a vector at the end, and then you take the tangential part of this, which means you basically project it onto the corresponding t sigma at the point P. So let me just make a small remark regarding the notation. So remember, we talked about this when we deduced this result in class. You're given vector fields on sigma, which means these are vector fields on the surface. to apply dy tilde on x tilde, you have to choose an extension. So this need not be a global extension. At whichever point you're calculating the covariant derivative, you have to extend it locally around that point. It simply means if you wanted to calculate it around P in sigma, you have to find an open neighborhood in R3 around P, extend the vector fields x and y to x tilde y tilde as vector fields on R3, and then compute this side. Okay, so this right hand side will not depend on the extension that you've chosen. That's a result that we proved in class as part of the proof that this identity defines the Levi-Civita connection on sigma. Okay? But this is just how you compute things. You basically compute it in the usual Euclidean sense by choosing an extension, and then you project it down to the tangent space of the embedded submanifold. So this is what we're going to do for a particular choice of a chart on a general surface sigma. All right. So are there any questions? Okay. So let us first write down the connection in local coordinates. And as before, we are going to make a choice. So this is the choice that we're going to make. We're going to assume that sigma in local coordinates around a certain point looks like uv f of uv. Although we'll not need this, but let me make a remark that sometimes you might want to choose your point to be 0, 0, 0, so that the origin is a point contained in the surface, and you might as well assume that 0, 0, f of 0, 0, which is also 0, is such a choice of a chart. So you are assuming that f of 0, 0 is 0. And this doesn't change any of the geometric computations, because given a surface, you can always translate it in R3 so that the origin is contained in the surface. Okay? But we're not going to make that choice. We just need a local chart to be of this form, uv, and the last coordinate is a function of u and v. The smooth function of u and v, since we're dealing with smooth surfaces. So the exercise, it's marked in red as usual for u, is to show that such a local coordinate system exists up to a permutation of the coordinates. Okay. So why do you need a permutation of the coordinates? Well, for simple reason that if you consider the sphere, the unit sphere in R3, around the north pole, you can solve for the z coordinate in terms of x and y, because z is 1 and x and y is 0. And in general, z square is 1 minus x square minus y square. So you can solve for z as the positive square root of 1 minus x square minus y square around the north pole. So your u is going to be x, v is going to be y, and f of uv is going to be square root of 1 minus u square minus v square. However, this is going to change if you go to the point 1, 0, 0, because at 1, 0, 0, you can solve for x in terms of y and z by doing the same thing. So it wouldn't necessarily look like x and y are the free variables. It would look like y and z are the free variables, and you're solving for x in terms of y and z. So up to a permutation, this can be done in this example, and the exercise is that it can be done in general. So as far as computations are concerned, it doesn't really matter whether it's uv f of uv or u f of uv v, as you'll soon see, but we'll make this choice. Okay. So this basically follows from the implicit function theorem, because you're in a two-dimensional submanifold of R3. So there'll be one variable which can be implicitly solved in terms of the other two variables, and up to a permutation, you can assume that's a third one. All right, so we can define a map phi from U to sigma. U is an appropriately chosen open subset of R2, and sigma is the given surface, and phi of U is going to be an open set in sigma homeomorphic to U via this map. So usually phi inverse would be the chart, and I'm going to make the abuse of notation by calling phi a chart. Okay? But typically it's from the manifold to Rn. Here we are choosing the opposite thing as a chart. Okay, so what do we do with such charts? Well, the obvious thing is you choose tangent vectors in the Euclidean setting. You see what they look like in the manifold setting, and then because the manifold setting has a way of measuring inner products, you can measure the lengths and angles between the standard vectors coming from the chart. So here, for example, you have del by del u and del by del v. These are the two standard vector fields, and you take the images of them under linearizing the map phi. So you look at d phi of del by del u. Well, that would simply mean that you take this function, v is constant, and then differentiate this under with respect to u, treating v as a constant. So the first term gives you 1, v gives you 0, and f u v, when you differentiate, gives you del by del u of f. And that I'm highlighting by a shorthand, so to speak, which is not really a new notation. You have seen this appear in calculus many times. F subscript x stands for del f del x. F subscript xx will stand for del 2f del x2. So this is the same notation. F subscript u stands for del f del u. Okay, partial of f with respect to u. Same with del by del v. You treat u as a constant. You differentiate the function under phi with respect to v. First term is 0. V goes to 1, and this is just del f del v, partial of f with respect to v. So we are going to quite often just identify the two tangent vectors because d phi is a linear isomorphism. So the original vectors are del by del u. This is 1, 0 f of u, but I'm going to call it del subscript u, and I'm going to call this one del subscript v. All right? Okay. So the first task that we have is to compute the connection for surface, and to do that we have to extend the vector fields 1, 0 f of u and 0, 1 f of v to a neighborhood of the surface. Remember, the surface looks like uv f of uv. So in general, the uv's are free variables, so I should be able to define what these vector fields are at a point of the form uv f of uv plus some variation in the z coordinate, because these are already free. So then we can calculate the standard covariant derivative with respect to R3, in R3, sorry, and then you project it down to the tangent space, all right? Okay, so how do you do that? Well, you basically define the extension del u tilde at a point uv f of uv plus z to be whatever it was at uv f of uv. Namely, it's the same vector irrespective of how much you have moved in the z direction. It is 1, 0 f of u, which is the same vector del u. And the same with the extension of del v. It is the same old del v, but you forget how much you have moved up or down in the z direction. So this is a very natural extension to choose, and because the computation doesn't really depend at the end of what extension you have chosen, this is a fair extension to choose. All right. Okay. Any questions? Okay. Okay. So let me show you a picture. So this is what I meant when I said that phi is not really a chart. Well, technically speaking, pi is supposed to be the chart that you usually see in manifold theory, namely that this curvy looking white shape up here is supposed to be a small piece of sigma, which has coordinates uvf of uv. So when you project uvf of uv to the first two coordinates by the map pi, that's going to be the chart. And the inverse of that is going to be the map phi, which we have been calling the chart for convenience. So this shaded quadrilateral is inside R2 with uv as the standard coordinate. So you have del by del u and del by del v as the standard global vector fields. And under d phi, this will go to 1, 0 f of u, 0, 1 f of v, and which we are denoting by del subscript u and del subscript v. So these two, the blue and the brown arrows, are tangent vectors for the surface. And this red arrow is supposed to be the normal, or supposed to be a normal, because you can take the cross product of two basis vectors, and that will give you a normal vector. And this is very specific to R3 because you have a cross product there. Same with these two examples. You could take these two tangent vectors, take the cross product. The red arrow is supposed to be normal to the surface at this point. Okay, is this picture clear? All right, so the vectors del u and del v forms a basis because it's the image of a linear isomorphism d phi of the standard basis vectors del by del u and del by del v. All right. So if you take the cross product, you can compute cross products pretty easily, and it turns out that the cross product has this as entries, minus f of u minus f subscript v 1. So this is not a unit normal vector, but it's a normal vector because by definition it's perpendicular to the tangent space. If you want to normalize this, you have to divide by square root of 1 plus fu square plus fv square, right? But we'll not do it right away. We'll use the fact that this is a normal vector field defined on this piece of sigma. Okay, all right. I hope the picture is clear. Okay. So what we want to do now, well, we simply want to compute, correct? So what do we compute? Well, you compute d of the extended vector field. Remember, del u tilde was 1, 0, f of u for coordinates of the form u, v, f of u, v plus z. So the first entry is 1, constant function 1. If you differentiate with respect to u, v and z, it will all give you 0. The second entry was 0. Again, it gives us 0. The third entry was f subscript u, which was del f del u. If you differentiate del f del u with respect to u, you get f of uu. With respect to v, you get f of uv. Recall that f of uv simply means del 2f by del u del v. And I can change the order of u and v because f is smooth. In particular, it's C2. And the last entry is 0 because f subscript u does not depend on z. And that was how the extension was chosen. Okay. What about d of del v tilde? Same thing. Del v tilde was 0, 1, f of v. So if you differentiate 0, it's 0. Differentiate 1, it's 0. If you differentiate f of v, with respect to u, you get f of uv. With respect to v, you get f of vv. And it's 0, the last entry, because f of v, or f subscript v, I apologize for saying f of v when I mean f subscript v or del f del v, that is independent of z by construction. Okay, so what we know, so to calculate this quantity, the covariant derivative or the Levi-Civita connection acting on del u in the direction of del u, it's going to be this matrix up here acting on the vector 1, 0, f of u, and then you project it down to the tangent space, correct? It's going to be this matrix acting on this vector, and t stands for the tangential part, meaning you have to project it down. Okay. All right. So fine. How do you compute this projection? Well, a tempting answer would be to say that you simply compute the dot product with del u, the dot product with del v, and then subtract off certain components. The catch here is that del u and del v are not orthogonal vectors. So they are not of length 1, which is not that big an issue, but they're not perpendicular either. So you have to do quite a bit of computations to compute the tangential projection that way. Okay. So the easiest would be to do what? The easiest would be to take the dot product with the normal, subtract off the normal component, and since there's only one normal here because we're in R3, this is a better choice. Subtract off the normal component, what you get is going to be the tangential component. Okay? So in either case, you should try this exercise, whichever way you like, but at the end, you should get that the tangential projection of this vector, it's 0, 0 f of u because I didn't do the matrix multiplication right away, but if you multiply, the only term that's left is the third row with this column, which is f of uu. So if you project 0, 0 f of u to the tangent plane, you're going to get this quantity. So if you ask why is this quantity a tangent vector, or if you have to check this, well, it stands to reason that it should be expressible as combinations of del u del v, and indeed it is. This expression can be simplified to be this quantity times fu del u plus fv del v. Okay, so we'll see this entry appear quite a lot, fu square plus fv square plus 1. So we'll have to give it a name in subsequent slides, but this is what you get. Okay, so essentially the answer to our original question is nabla del u along the direction del u is going to be f of uu divided by this quantity, which is symmetric in u and v, times this vector, which is symmetric in u and v. This is also a vector that's going to appear quite a lot. So just take a mental note of this before I move on to the next slide. All right. Okay, so allow me to move on. So we are going to introduce the notation as I just remarked. We are going to call this vector field, which is defined on u or phi of u by xi, and this function by alpha. Okay? So the exercise for you now, if you followed the calculation earlier or the suggested method, you basically have to show that if I calculate nabla del v with respect to del u, or covariantly differentiate del u with respect to del v, I would get the same answer, which is this alpha quantity at the denominator, FUV in the numerator, times xi. So note that nabla del u del v is equal to nabla del v del u. Okay? So I'll give you guys a moment to think of why that's the case. So you should think of where this connection comes from, right? So this connection is the Levi-Civita connection, meaning it's torsion free. And since we are working with coordinate vector fields, torsion free for coordinate vector fields means, because the Lie bracket of coordinate vector fields is 0, that simply means nabla xy is nabla yx by torsion freeness. So you don't really have to calculate this term. It will turn out to be equal to this, which is this. Okay? But note the symbolic sort of symmetry that f of uv is f of vu, because f is at least c2. So del 2f by del u del v is del 2f by del v del u. So even if you had computed this, you basically get f subscript 2 indices that appears here, which in this case it doesn't really matter. We had f uu before, but that was because we did nabla del u del u. So now you see a pattern, and in fact, if you compute nabla del v with respect to del v, you'll get f of vv times the vector field xi divided by alpha. It's a very nice formula that you get. You can remember one, or you can deduce one, and then you see that the exact computation works out, and it simplifies to something very nice. All right. So this is good. Okay. So I wrote this sentence. So see, it's very natural to ask the following question, that you have these operators, nabla subscript x. What kind of an operator is it? Well, it takes a vector field as an input, outputs another vector field. Okay. So nabla subscript x feeds on a vector field y, and the output is nabla y with respect to x. This is not a C infinity M or C infinity sigma linear map, because with respect to y, this satisfies the Leibniz rule. This is not C infinity linear. However, it's still a vector field. So you can think of these as operators, and you can ask whether these operators commute. Like we said that the Lie brackets of del u del v commutes. So it's very natural to ask whether this commutes, and if it does not commute, what exactly appears as the discrepancy. And this is a very natural question to ask algebraically, also geometrically, because last time we had seen that the failure of parallel transports to commute with a little bit of analysis led us to the notion of torsion from a purely geometric perspective, following Cartan's ideas, right? So this is the same kind of question. Perhaps you discover something geometric by analyzing the commutativity, or the lack of it rather, of these two operators. So we want to check for commutativity. So in particular, it makes sense to ask what this thing is about a particular vector field. So let's say you want to compute the commutator as an operator. The first thing would be you want to evaluate this on certain vector field. Namely, you want to evaluate this on del v and del u, right? So what is the commutator of two operators? Well, you know from linear algebra, commutator of AB is AB minus BA. But that is because given a vector, B acts on B and then A acts on that BV, and then you subtract off B acting on A acting on B. So it's the same procedure. The commutator of two operators is defined this way, which means you have to compute this whole thing on del V. And del V, remember, was the vector 0, 1, f of V, f subscript V, sorry. Okay, so let's compute this. So, of course, let's look at the first term. This is going to be nabla del u of nabla del V, but we just have it upstairs, right? So nabla del V is nothing but f of VV alpha inverse psi. That's why I've written it here. Now what about this term? Well, this is minus nabla del V of nabla del U del V, but that is FUV alpha inverse xi. That's this formula up here. Okay? So this is the first step. So now you basically have to use the fact that now we are done using any kind of C linearity because there's nothing else you can use. Now the top thing here is a vector field times a function. You have to use the Leibniz rule for both these terms. All right. So I'll put the next equality in, and hopefully you can see what's going on. So let me add all the four terms. So we expect four terms. One is going to be you pull this function out, and then nabla del u acts on xi, or del u acts on the function and the xi stays fixed. So that's the Leibniz rule on the first term. Similarly, the Leibniz rule on the second term. So you pull out the function, then del v acts on xi, or del v acts on the function, xi stays fixed. So I hope this is clear, right? Okay, so we are going to simplify this in the subsequent slides and arrive at something interesting. So let me proceed if there are no questions. So far we haven't started the computation, but now you have to compute what this quantity is. Okay, and remember that alpha is this number, fu square plus fv square plus 1, and xi is this vector field fu del u plus fv del v. All right. Okay, there are no questions. Let me start the computation. So this is what we had. The commutator which we want to check whether it's 0 or non-zero, acting on the vector del by del v, is going to be fvv over alpha, nabla del u acting on xi, minus, this is the same kind of term coming from the second term. So this is minus fuv over alpha, nabla del v of xi. And then you have the other terms where the xi was fixed. And again, this is something I'll leave as an exercise for you to simplify. That if you simplify, this is what you'll get. Okay. Okay. So far we haven't really done anything apart from simplifying a little bit. Okay. So what happens here? Well, let's leave this as it is. I'm claiming that this term here, when you compute, so you have to compute del u of this function minus del v of this function. And when you do that, it's a couple of lines, one for each of the terms. It simplifies to this term. And this is in red because it's a simple computation that you should check. All right. Okay. So you basically get a term which should be familiar looking. Namely, if you have dealt with the Hessian of a function, then this is the determinant of the Hessian, right? And this is going to be one of the terms which is going to stick with us for almost the remainder of the lecture, along with the term fu square plus fv square plus 1. These are the two relevant terms. And for those who have seen or remember these kind of terms appear in the theory of surfaces, just hold your thought for a few minutes. We'll get there. No wonder these things are appearing, because these things also appear when you discuss curvature for surfaces. And that's what we are going to try to do as well. Okay. So anyway, so you simplify. So what happens? You use the Leibniz rule. So either fu pulls out and then it's nabla du du, which is fu by alpha xi, or the del u comes out and then it's del u of fu. But del u of fu, remember, is d2f by du2, which is f subscript uu. So these two comes from the first term. All right. Okay. Now what about the second term? Well, it's fv and then del u del v, which is fuv by alpha xi, or the del u acts on fv, the del v stays fixed, which is fuv del v. Again, fuv means del 2f by del u del v. Right? Okay. So what about the next term? Well, something similar happens. You apply the Leibniz rule to this term, you get these two terms. And this is best if you go back and do it on your own and then try to check whether it matches up with what we're discussing here. And it's best to do it by yourself rather than me saying out all these things, because it's just a bunch of symbols and equations. And I want us to verify it on your own at the end of the day. Okay. So anyway, so I'll not bore you with this. So this is what you get from the first line. Okay, and the last term just stays as it is because I've already simplified this. So now if you look very closely at these 10 terms, 4 in the first line, 4 in the second line, and 2 in the second line, and the third line, sorry, some terms cancel. Okay, so we only get these 4 terms. So which terms cancel? So there are cancellation in pairs actually, and if you look closely, you will see that this term, the 4th term, and the 8th term cancel. Okay. Similarly, the 3rd and the 7th, they cancel because there's FVV here, there's FUV, there's FVV and FUV, and this comes with a minus sign. And there are some cancellations among the xi terms. If you combine the xi terms, if this was a -2, but now it's only a -1, which means you combine these xi terms, that contributes a +1, and this is -2, that essentially gives you a minus. And the du's combined to give you this. Okay, so there's a simplification that I'll ideally leave you to check, but this is what we get. Okay, so the Hessian, and I mean rather its determinant, appears in 2 places. All right, so let's move on. So what do you get? You basically get this quantity from the last line of the previous slide. You can simplify this. If I combine the FUV, FVV minus FUV square, the determinant of the Hessian, and then I have alpha square in the denominator, then this is what I get. Okay. Now you can simplify this even further, and what you get is this quantity, which is not that bad. It's something involving del U and del V naturally, but the coefficients are going to be somewhat nice in the sense that do represent something meaningful. I mean, they're definitely algebraically not too bad. So the exercise for you now is to compute the same operator, the commutator, acting on del U by the same process, and chances are you can even reduce some of the lines because you know what exactly the simplification is or what cancellation might happen. So I'll leave it to you to check that. But what I would like to do right now is, so it's pretty clear that this operator, first of all, will not be 0, because this operator being 0 means they commute, but this will not be 0 because if you hit this with the vector field del B, then you get this vector field, and this vector field will typically not be 0. Why? Because if this was, see, this term is never 0. This is always at least 1. This term could be 0, in which case either FU is 0 or FV is 0. And the only way this whole thing is 0 is precisely when this becomes 0. Okay? But that basically means that the Hessian, the determinant of the Hessian is 0. And for most examples that you might compute, the sphere, the parabola, the revolution, and so on, you assume that FU, FV in the second derivatives are not entirely 0. So nonetheless, this is typically not going to be 0 unless F has a certain structure, namely, as we'll see, unless F is of a very special form. So that answers our question whether this commutator is 0. It's not 0 in general. However, we are always better off working with functions or scalars rather than vector fields or vectors. So how do we get a vector out of, how do you get a scalar out of a vector? Well, you can take this vector that you have computed and you can pair it with del by del U. You can pair this with del by del V. You might ask, why didn't we do that? Well, we didn't do that for a reason, and the reason will be clear at the very end. But even if you did do it right now, if you're adamant that I want to compute this quantity with del V, you'll see that this will turn out to be actually 0. So it wouldn't really give us anything interesting. Nonetheless, let's take it in this order for reasons that will be clearer in this lecture at the end and the subsequent lectures. So what do you have to do? Well, you have to basically take this vector, dot it with del U, which means take the first vector, dot it with del U, take the second vector, dot it with del U. This is a constant, so that can be pulled out. Okay. What do we get? Well, remember del u, the dot product is 1 square plus f of u square, f subscript u square, because del u was 1, 0 fu. Same with del u, the dot product will give you fu fv. So it contributes fu square and fv square. Now what is this quantity? If you simplify, this quantity is going to be 1 plus fu square plus fv square, right? Good. So this is also the same thing that we have seen appear over and over again. This is basically alpha. So actually this simplifies. This becomes the determinant of the Hessian divided by alpha. Okay. So far so good. Any remarks? Okay. So let's proceed further with this. Okay. So let's write down what we had in the last line of the previous slide. This is what we had. And remember, we called this alpha, and we had intentionally simplified this to 1 plus fu square plus fv square. But let me get back to the non-simplified version and precisely write it this way. We'll see why in a moment. Okay. So, okay. So we are going to keep this form in front of us because this is the form that's going to appear very soon. How are we going to get this form? Well, remember, we have a Riemannian metric on sigma induced from the Euclidean metric on R3. Once you have a Riemannian metric, that metric gives you a matrix. Namely, you take the tangent bases that you have chosen, del u and del v. Take the ijth entry of the matrix to be the inner product of del by del xi with del by del xj. So that's what. So the matrix G as a function of uv is going to be the entries given by inner product del u, del u, del u, del v, del v, del u, and del v, del v, right? All right, good. So what is this? Well, that's precisely the 4 entries that appears in the denominator up in the identity above. Fu square, fu fv, fu fv, fv square, because G is a symmetric, I mean, it's a Riemannian metric, so it's symmetric. So the matrix is also symmetric. Okay. So what you see appear at the top is the determinant of the Hessian. What you see appear at the bottom is, in the denominator, to be precise, is the determinant of the matrix, right? Good. So G, thought of as a metric or as a matrix, has determinant alpha. All right. So what do we conclude? Well, we conclude that if I take this quantity, divide out by the determinant of G, I basically get the determinant of the Hessian divided by alpha squared. And since we have been repeating this over and over again, I think most of you probably by now have concluded or do remember this formula from the theory of surfaces, that this is nothing but the Gaussian curvature. Okay. So the reason why I have to divide by determinant of G is that the basis del u del v for the tangent space is not an orthogonal basis. So their lengths are not 1, they're not necessarily perpendicular, so you have to normalize. If it was an orthonormal basis, then this would be 1, 0, 0, 1, so determinant G would contribute nothing, so it would be whatever you obtained earlier. But because this is not an orthonormal basis, we have to rescale by normalizing by determinant of G. And if you do that, you get this formula, which is precisely the Gaussian curvature, computed in the local coordinate system, UV, FUV. Okay. All right. So are there any comments or questions so far? Okay, so let's move on. So we are going to make some further observations and connect the curvature to forms, because moving forward, that's something which we'll use on and off, and even otherwise, apart from this course, if you do more general courses on topology and geometry, you're going to need this formality. So let me move on. So I want to make a remark before I end up connecting the connections to differential forms to curvature. So we know the Riemannian metric sigma in a local chart. So instead of calculating the Levi-Civita connection by this process, you could also calculate the Christoffel symbols, which simply involves derivatives of the matrix that we just saw, and then have to write down the Christoffel symbols. Once you have the Christoffel symbols, you can then write down the Levi-Civita connection. Okay, so you can do it that way as well, because you know the matrix, you know all its derivatives, and hence you can combine them in the way that you should to get the Christoffel symbols, which then gives you the Levi-Civita connection. So the exercise for you is to compute that and show that the Christoffel symbols also behave very nicely symbolically. So if you're calculating Christoffel symbols with u and subscript uu, this will be the same old alpha, fu square plus fv square plus 1, or determinant of g. But on the top you have fu and fuu. And as you read the remaining equalities in the list, they all look the same, in the sense that the pattern can be read off from whichever is the superscript and which two indices appear in the subscript. Okay. So there's something missing here, that if you have gamma VVV, what should it be? Well, that should be FVV divided by alpha. So the numerator is entirely symbolically determined by reading off which is at the top and which is at the bottom. The denominator is just determinant of the matrix, the normalizing factor. Okay. So this is also very nice. So I hope all of you go back and do this. Okay. So you can recover the Levi-Civita connection for surfaces either way. Okay. So let me make a remark about this, one of the great discoveries of 19th century mathematics, Gauss's theorem egregium. And we'll not talk a lot about this because this is something that was covered in the course on geometry of curves and surfaces. I just want to mention this along the way because it's a result worth mentioning. It's a celebrated result. So it basically says that isometry between surfaces, of course in R3, preserve the Gaussian curvature. Well, what does it mean informally? It simply means that if you were a smart inhabitant living entirely on the surface without knowing where the surface is, how it's living in R3, you could determine the Gaussian curvature of the surface by making local measurements, okay, angles, lengths, entirely on the surface. That's the point of this theorem, that it's intrinsic, the Gaussian curvature. You may have no idea of the global shape of sigma, you may not even know about the shape operator, but you might still be able to calculate the Gaussian curvature. Okay. So in other words, you can recover these things entirely from the metric itself, okay? The curvature from the metric. Okay, so I want to do a couple of examples highlighting this, and then we're going to finish off with the connections of curvature to differential forms. Okay, so let's start with the canonical example of a flat surface, the xy plane. There's one chart, uv goes to uv0. Right? As before, this is the reverse of the chart, but this is going to be my chart. Okay? So we have seen that the Christoffel symbols vanish. So the Gaussian curvature will turn out to be identically 0. Okay? Even by our formalism or the other way around. So we consider an infinite cylinder. This is a cylinder with x-axis as its axis of symmetry. And it's a unit circle in the YZ plane translated along the x-axis. So you consider a horizontal strip. I'm sure all of you can see the picture. So this is a curved strip colored orange, which is lying on the top sort of curved part of the cylinder, so to speak. So this is the origin. So this point here, which the z-axis intersects with the cylinder, is the point 001. Okay. So you want to measure the Gaussian curvature of this. So how do you do that? Well, you choose a chart around 001. What could a chart look like? Well, a chart would simply look like you choose the xy coordinates to be the free variables. uv goes to u comma v, and how should z be defined? Well, remember y square plus z square is 1. So z square is square root of 1 minus y square, and our y is v. So z is square root of 1 minus v square, and we've chosen the positive square root because z is being solved around 1, around the point 001. So this is the function. So we know what f is. F is independent of u, which means del f del u and all u derivatives of f, higher powers, they are going to vanish. So if you calculate the Christoffel symbols, the only term that you expect, if you go back one slide here, see the only term that you expect to survive, it's not here on this list, it's gamma V subscript VV. Anything which has a U either on the top or on the bottom will not survive, whether it involves some partial derivative of f with respect to U or second order derivative with respect to U, but f is independent of U. Okay, is that clear? So that's a simple computation. In fact, you can calculate this function and calculate its second derivative up to V. And so you can show that the only non-zero Christoffel symbol is gamma V VV, which is also something very nice. It's V over 1 minus V squared. Okay. So that in particular is going to imply that the Gaussian curvature is 0 by our formula or otherwise. Okay. So why does that determine the Gaussian curvature for the whole cylinder? Well, remember, an isometry preserves Gaussian curvature, that is Gauss's theorem agranging. So if you rotate about the x-axis, you can go from 0, 0, 1 to any point of the form 0 cosine theta sine theta, correct? So that says that the entire unit circle at x equal to 0 has Gaussian curvature 0. But then you can translate along the x-axis. So along with the rotations and translations, you can go from any point on the cylinder to the point 0, 0, 1. All of these are isometries, so the Gaussian curvature everywhere is 0. All right. So that takes care of all points. You don't have to do it separately at every point. So that says that the cylinder and the plane R2, the xy plane, they both have Gaussian curvature 0, although they are not geometrically the same shape. All right, so I want to talk a little bit about one more thing before we go on to the forms. So remember, we have seen in a course on geometry of curves and surfaces, in the surface section, we have seen that there's a very famous theorem called the Gauss-Bonnet theorem. And let's state that for an oriented surface means that there's a normal vector field defined over the whole surface. So a Mobius band is one where you cannot define a normal vector field over the whole surface. So that's what an orientation is for a surface in R3 for us. We're going to assume that the surface is compact without boundary. So every point has an open neighborhood around it which looks homeomorphic or diffeomorphic to an open ball. So there's no boundary and it's compact. Compactness is important because we're going to integrate something on the surface, and without compactness you may not be able to integrate a general function. So we can integrate this Gaussian curvature using the surface area or the surface form and obtain a number. So this is the famous Gauss-Bonnet theorem. If you have a closed oriented surface, closed here simply means it's compact without boundary. If you have a closed oriented surface, you integrate this Gaussian curvature with the area form over sigma, what you get is a number. The key output or key sort of implication of this is not just that you obtain a number, you obtain a topologically relevant quantity, which is Euler characteristic of the surface. That's a topological invariant. The left-hand side is something dependent on the metric and the curvature and on the geometry. So there is a mixture of geometry and analysis. The right-hand side is topological or perhaps even combinatorial, because you can calculate the Euler characteristic by chopping the surface up into vertex, edges, and faces or triangles. And the remarkable thing is that the integral, which a priori could have been any real number, is somehow quantized in the sense that it's integer multiples of 2 pi. It's not an arbitrary real number. So this is a very, very beautiful and rather deep, in my opinion, result. Deep because it is connected to a circle of ideas which goes deeper and deeper. Okay. So this is an important statement connecting geometry and topology. It can be generalized to surfaces with boundary, but then you have to contribute an extra term which talks about what would be the corresponding integral on the boundary. It has to be some sort of an integral or contribution from the boundary term, and then you have to rectify it also with angle defects on the right hand side. It can also be generalized to even dimensional manifolds, and hopefully we'll have time to talk about this last bit in the last lecture on curvature. So this is related to a generalization called Chern-Gauss-Bonnet theorem. Okay. So so this is where I would like to stop regarding the review of the classical discussion. I want to end with a small discussion on differential one forms and differential two forms and how it relates back to Gaussian curvature. But keep this example in mind because we're going to use this in the very next slide. Okay. So are there any questions? Okay, so here you should note one thing, that we are integrating something over a surface. Typically, how you integrate a form over a surface, or a two form over a surface to be precise, is that you have to break it down into open sets, use a partition of unity where you have local coordinates, and then this looks like some function du dv, and you integrate that function over the open set. So this is a two form, and in fact something more is true. This is a closed two form, because if you take d of this, it's a three form, and there are no non-zero three forms on a two-dimensional manifold. So it's evidently a closed two form, which encodes the Gaussian curvature, right? That's the starting point for the next. So there's a natural thought that you should think about. It's a closed two form. If we just started off with the Levichovita connection and did a lot of things taking cue from what we talked about earlier in the last class and the class before, can we recover or discover this two form from the concept of connections and associated constructions? So if this question sounds a little vague, let me break it down. Okay. So let's try to see what one could mean by coming up with a one form or a two form from the notion of connections. Remember that we had talked about extending this Levichovita connection to PQ tensors. How did we do that? Well, we said pretend that the Levichovita connection really acts on vector fields, and the output really can be thought of as a 1-1 tensor, because then when you input x here as a superscript, the 1-1 tensor feeds on that vector field and gives you a 1-0 tensor, which is a vector field. So remember, a 1-1 tensor is nothing but a section of Tm tensor T star M. So it basically looks like a linear combination of vector field tensor one forms and a finite linear combination of them. In our case, this nabla of del u is going to be a 1-1 tensor defined on phi of u. But that means I should be able to express it in terms of the tangent basis vectors, which is del u tensor a one form plus del v tensor some other one form. Because it is a tensor, whatever functions that appears here, I can absorb it in the one form part. Okay. Similarly, nabla of del v can be expressed as del u tensor one form plus del v tensor another one form, and I'm indicating these one forms by omega with a superscript and a subscript, and this is chosen so that this matches up with the Einstein summation convention. So that if I put dot here and dot here, that means the u is fixed, the u comes from this u, and you sum over the dot, which runs from u through v. It runs through two variables. Same here. The lower v corresponds to the lower v here, and otherwise this dot will be either vv or uu. Okay? So this is how the notation is chosen. So at this point, you might ask, okay, how do we determine these one forms? We know that they exist because of what we discussed last time, but how do we determine them? Well, how should you determine them? Remember, if you plug in del by del u here, that should give us the old Levichovita connection of del by del u with del u with respect to del u. But that would mean you have to input del u to this one form. What you get is a function, and a vector field tensor of function is nothing but the vector field times that function. Same with inputting del by del u here, or del u here. That's going to leave you with a function, and then it's that function times del v. Right? So that should happen. So remember, these are defined precisely by the requirement that when I input x, this is something we know, and this should match up with whatever one forms you're choosing. When you plug in x, this is a function, and then this right hand side should match up with whatever we know to be the left hand side. So I'm just recalling how we define this connection extended to PQ forms. Okay. So in particular, that means what? That means if I wanted to calculate omega UU, for example, it's a combination of du and dv because it's a one form. How do I find the coefficients of du and dv? Well, if omega uu is f du plus g dv, how should I recover the f? Well, I have to hit omega uu with del u. So the du acts on del u gives me 1, and then f comes out, and g dv acting on del u is 0 because dv acts on del u is 0 because du dv is a dual basis to del u del v. So I have to hit this with del u to recover f. Correct? Similarly, I have to hit this with del v to recover g. Which would mean what? Which would mean if I hit this with del u, which means I put del u here, whatever shows up, I have to look at the coefficient of del u in the expansion of nabla del u. That's going to give me the f. Clear? Similarly, I hit this with del v. So nabla del u with respect to del v, and I look up the coefficient of del u there. That's going to give me the g part. So I hope this is clear. Okay? Just mentally, it seems like there are too many symbols floating around, but it's really something implicit and easy at the same time. It just looks a bit difficult the first time you see. So the coefficient of du is the coefficient of del u in nabla del u. And the coefficient of dv, as I said, is the coefficient of del u in nabla del u with respect to del v, because this is the input vector field that you're feeding to the one forms. So this is something you can check, and I'll not bore you with saying what goes where, because it's better if you just write it down on a piece of paper, stare at it for a few seconds, and you'll get it immediately. So it turns out omega subscript u superscript u. Just hold on a second. Yeah, so sorry about that break. So coming back to what I was saying, you have omega uu. So one can show that this is nothing but fu by alpha dfu. Okay. So let me break down what dfu means, and all of you know this very well because you have had a course in differential geometry. But dfu simply means that the Dirac differential of a function, which means it's del f u del u du plus del f v, del fu del v of del by del v of fu times dv. So if you expand it out, this is what you'll get: fu du plus fu v du. Okay. Nonetheless, the point being that there's a symbolic pattern which appears even here. Okay, the u on top goes here, the u at the bottom goes here. Same thing happens to omega vu. It's going to be fv over alpha dfu. Same with omega uv, fu on the numerator, dfv also on the numerator, but that's the one form part of it, and alpha stays fixed throughout the whole discussion. Same with omega vv, it's fv dfv divided by alpha. So it's a very nice example for this particular choice of charts because all the things have a recurring sort of pattern. You can read off the coefficients. Once you have done the calculation once, if you remember one set of formulas, you can recover the others just because of the pattern. Okay? So is this clear? So we know what the one forms are, all right? Good. So we get 4 one forms. So what can we do? Well, we could do lots of things with one forms, but because of how we had denoted these one forms, they had a superscript and a subscript. Probably some of you have got the hint already that we want to arrange them as a matrix. It's going to be a 2 cross 2 matrix because there are 4 entries, and as the footnote suggests, the ijth entry is going to be given by omega superscript I subscript j, meaning the superscript is going to stand for the row, the subscript is going to stand for the column. Okay. So let me show you what the matrix looks like. So I'll denote this matrix by omega. This matrix actually has a name. I forgot to write it in the slides. This is called the matrix of one forms associated to the connection nabla, of course, in a local coordinate. So in general, if you are in a n-dimensional manifold, you expect it to be a n cross n matrix of one forms. In our case, this is a 2 cross 2 matrix because we're dealing with surfaces. All right. Okay, so this is alpha inverse FU DFU, alpha inverse FU DFV, alpha inverse FV DFU, alpha inverse FV DFV. Good. So at this point, you can, or you should be asking yourself the question. Remember, we had talked about KDA, that was a 2 form. Now we have ourselves a matrix of 1 forms. How do we obtain a matrix of 2 forms, and whether we can combine all of this to get an actual 2 form which resembles the 2 form KDA? Well, I think most of you probably know this already, that given a form, you can always take the Dirac differential D. That's going to give you a form 1 degree higher. So you can do the same thing for the matrix. Doing it term by term, it gives you a 2 cross 2 matrix of 2 forms, correct? Fine. Is there anything else that you can do? If you think about it, for a single 1 form, taking wedge product of a 1 form with itself will give you 0. Nothing interesting because it's Q-symmetric. However, in this case, you do not have a single 1 form, you have a matrix. So what you could do ideally is you could multiply the matrix with itself, but when you multiply the entries, you multiply them using the wedge product. And that has a chance of being non-zero because now we cannot really use skew symmetry of matrix multiplication, because matrix multiplication, remember, is not symmetric. But so if you multiply it one way or multiply it the other way, they'll not be the same. So you can try both of them. So let's try the first one. What is d omega? Well, d omega is simply going to be this. So why is it this? Well, remember that d square is 0. That's one of the key properties of the Dirac differential. So you take d of this, by product rule, it's going to be d of the first term, which is fu by alpha, times dfu, plus you leave alpha inverse fu, and then it's d of dfu. But because d square is 0, you only have 1 term for each of the terms. So that's this quantity. Okay, so this is a 2 form. All of these are 2 forms. Okay, all right. What do you get for the omega wedge omega part? Well, this is also something you can check. If I multiply omega wedge omega, that means I multiply the 2 matrices, but the entries are multiplied with respect to the wedge product. So when I write this here, I mean dfu wedge dfv. And again, you can check that each will only have 1 term that appears, and there are some signs that appears here because of skew symmetry of the wedge product. So everything here is written in terms of dfu wedge dfv, all of them. Okay. So this is basically a matrix with functions and a common 2 form dfu wedge dfv, which comes out. Is that clear? Okay. So the exercise that I'll leave you to check, again, it's a couple of lines, is that if you simplify d omega, meaning you compute this thing, you'll see that this is what you get. So again, you get dfu dfv as a common 2 form, but the entries that you get are of this type. So the first entry is 2 fu fv by alpha square. The 2th entry is minus 2 fu fv by alpha square, whereas the entry up here is 1 minus fu square plus fv square, whereas here it's minus of this. Okay, but the fu square and the fv square change signs. Okay, so far so good. So we have 2 matrices of 2 forms. What can we do? Well, the best thing would be to combine them in some way to get one single matrix of 2 forms. Okay? So I'll make a remark here, not in the slides, but just verbally, that depending on the notational choice you make and the convention, sometimes people take d omega minus omega wedge omega, and sometimes people take d omega plus omega wedge omega. We're going to make the latter choice because of how we have chosen things. That depends on whether we think of vectors as columns or rows. So for us, that's going to be the choice because we have already chosen the notation omega, so that omega ij is of this specific form, that the rows and the columns correspond to superscript and subscripts. Okay. So that's just a notational remark, if you want to call it that. So we'll form this matrix of two forms, d omega plus omega H omega. What does it look like? It looks like this. Why? Let me go back one slide. If I add these two, what do I get? There's a 2 here, there's a minus here, there's a cancellation. Similarly here, 1 minus fu square plus fv square, the fu square cancels with the fu square. Similarly, the fv square cancels with the fv square. So I'm left with 1 plus fv square, 1 plus fu square with a minus. The last term, minus 2 with a plus 1 is minus 1. Okay. So pretty clear. So this is what you get. All right, so this should look familiar, right? If I factor out the dfu, dfv, I get a matrix which looks very similar, because if I take the determinant, it looks like fu square, fv square with a minus sign, plus 1 plus fu square, 1 plus fv square. So that is basically 1 plus fu square plus fv square, right? So we're seeing kind of similar things appear like we have seen half an hour back. So this is called the curvature matrix of the connection. And this works in the general setting also. You'd simply get an n cross n matrix of two forms if you're dealing with an n-dimensional manifold. All right. Okay. So this is a formalism attributed to Cartan, Elie Cartan, where he tries to think of this curvature matrix or the connection matrix as controlling how the frame rotates as it moves along a curve or along a geodesy. So it's related to the notion of torsion of how a frame rotates. But that was in the language of parallel transport. This is in the language of a matrix of one forms or a matrix of two forms associated to the matrix of one forms omega. So this is called the curvature matrix. Okay. And the reason why it's called the curvature matrix will be hopefully and abundantly clear in a few minutes. Okay. So before we say anything more, let's just simplify this two form that has been popping up, dfu, dfv. What is that? Well, recall dfu, as we discussed, was fuv du plus fuv dv, wedge fuv du plus fvv dv. So if you calculate the wedge, what does it become? It's fuu fvv minus fuv fuv. That's because du wedge du is 0, dv wedge dv is 0. So up to a sign change, you only have du wedge dv, and this is the factor. So that's good. This is the determinant of the Hessian, and whatever else that was showing up here was precisely something that was appearing in the denominator of the Gaussian curvature, right? So we're getting closer to something. Okay, so now what can you do to this? Well, you could basically say, I have omega, it's a matrix of two forms. What does a matrix of two forms do? Well, you have to input two vector fields to that. And when I input two vector fields, what I get is an honest matrix, 2 cross 2 matrix of functions. And then I can evaluate such a matrix on two vectors, one as a column, one as a row, and what I'll get would be a scalar or a function, right? So let's do that. Let's evaluate omega on du, del u, and del v. Remember, when I evaluate omega on del u, del v, I'll be evaluating dfu, dfv on del u, del v, which means when du, dv acts on del u, del v, that simply gives me 1. So I'll simply get 1 here. This term goes away. I'll get 1 here. I'll get 1 here. I'll get 1 here. Along with this factor, of course. So what do I get? I basically get the same factor which I've pulled out, and alpha square is this. And then what's left inside is fu fv, 1 plus fv square, minus 1 plus fu square, minus fu fv, correct? Okay, so this should look familiar. See, this already looks like the Gaussian curvature up to these entries. Okay? So you cannot quite take the trace of this because the trace is 0 and the curvature usually is not 0. But remember, this is a matrix, and what you can do to get a scalar out of this or a function is you evaluate this on tangent vectors. So how do you evaluate the Hessian on tangent vectors on a pair of them? Well, one of them is the column, one of them is the row. So we'll do the same thing like we did on the commutator of nabla del u, nabla del v. We simply evaluate this on the column tangent vectors. we're going to evaluate this on del u and del v. But remember, we're writing this in terms of the ordered basis, which means del v is simply the vector 0, 1. Del u is simply the vector 1, 0, because it's already in terms of the basis. So let's do that. Okay, so remember this matrix. This is the determinant of the Hessian divided by alpha square, and these are the entries that shows up, and we're going to evaluate this on del v, which is 0, 1 as a column. So let's do that. So what do we get? We get the Gaussian curvature, fu, fv, and all the other entries acting on 0, 1. What do we get? Well, we simply get this and this. But then if I rewrite them in terms of the basis of the tangent space, excuse me, what I get is k1 plus fv square del u, that's the first coordinate, minus k fu fv del v, that's the second coordinate, correct? Okay. So how do I get a number out of this object? Well, I dot product with a vector field. What vector field can I choose? Well, we choose del u, correct? Remember, del u was precisely the choice when we calculated nabla del u, commutator nabla del v with respect to del v, and then inner product with del u. So let's do that. So, okay, so before I do that, if you compare your answer, which you should by going back a few slides, you can show that this thing that we had computed was exactly this. Okay. So this operator, whatever this matrix of two forms, now it becomes a matrix because I've input del u del v. This acts on del v in precisely the same way that the commutator acts on del v. More generally, they act precisely the same way. So they are the same operator. Okay. One of them is an operator where you input a vector field, gives you a vector field. You can think of this as a matrix. So a matrix is also an operator. It acts on vectors and gives you vectors. But now we're pretending the vectors are written in terms of the standard basis del u del v, in terms of coordinates. So they're the same operator, which is a nice observation and actually quite key in the subsequent lectures. So the remark that you should keep in mind is that for a general vector field x and y, for a pair of them, what you really get is this connection matrix, or the curvature matrix, sorry, is really this object. Okay. That's because we chose our x and y to be coordinate vector fields which commutes with each other. So the Lie bracket was 0. So the last term wasn't visible. That's why they were equal. But in general, this is the term that you would want to compute. And we'll talk more about this in the next lecture at length. This is the thing that you want to really understand and calculate, and that turns out to be equal to the matrix of two forms in the same formalism, in generality. Okay, so this curvature matrix is actually a key ingredient to study connections on vector bundles, principal bundles. If you're inclined towards physics, then in gauge theory they appear all over the place. So this is very important tool, actually a key computational tool for a lot of reasons. This matrix omega as well as local computations. But this right-hand side is going to be what's going to occupy us for the remaining 4 or 5 lectures. Okay. So let me stop there. Just go through the computations. Some of you have already done so because I had sent you the slides earlier. Make sure you understand them. This is simply me trying to recast the classical theory of surfaces from the perspective of connections and related constructions. We're going to now start the actual theory of Riemann curvature and various other curvatures associated with it from the next lecture. So that this gives us a motivation and a stepping stone for studying something like what's defined on the right hand side, so that it doesn't come as a shocker as to why we would like to study this. Well, there's enough reason now that we'd like to study this, motivated by what happened in the case of surfaces and Gaussian curvature. So if there are no questions, let me stop here.